So it's my great pleasure to introduce Professor Pierre Mathieu from Marseille. He's visiting us for a month as a distinguished professor, and he will give a series of lectures, 5 lectures, as announced today in person. The title of his lectures is Fluctuation, dissipation, dissipation relation for reversible diffusion in random environment. Please.
Okay, thank you. Thank you for the introduction. Thanks for the invitation. Okay, so as Takashi was saying, there will be 5 lectures, and I was asked to give introductory and elementary first 2 lectures, and then, if I correctly understood, from the 3rd lecture on, I can move to more technical aspects. So I will try to do that. So today's lecture is going to be very introductory. It's going to be introductory in the sense that I'm going to introduce the objects I want to look at, so diffusions, reversible diffusions in a random environment, and I will introduce the questions and some well-known results. I will recall some only quite well-known things. And, but it will introduce some notation and some spaces which are needed in the rest of the talks. And I'm not going to spend too much time today on the motivation. I postpone this discussion to the 2nd lecture. So the 2nd lecture will be also introductory, in the sense that I plan to talk about the motivation and in particular, I mean the motivation for the results and for the questions we are interested in. Okay, so I want to discuss reversible diffusions in a random environment, and let me write some equations. So I'm interested in reversible diffusion processes, reversible diffusions in RD, and so they are given by stochastic differential equations of this form. So the diffusion satisfies an equation with some noise term, sigma xx at time t, and there is a Brownian motion and a drift term, b xx time t dt. And the small x indicates the fact that the diffusion starts from point x. So x at time 0 is x. So throughout the course, I will make a number of assumptions. So first of all, I want to consider diffusions in a random environment so that the coefficients of this equation actually depend on some random parameter omega, and therefore the solution also depends on omega. So there are omegas everywhere. So we have random coefficients. Random coefficients, sigma omega and d omega. And the standing assumption is that the law of these coefficients is stationary and ergodic. So let us write Q for the law. So the law, I denote it with Q. And I'm assuming, this is my first assumption, that Q is stationary and ergodic. Ergodic. Now, I'm also considering only the reversible case. So the reversible case means that if there is some relation between the drift and the diffusivity coefficient sigma. So if I write A omega for the square of sigma omega, then B omega is, I guess, 1/2 the divergence of A omega. So Another assumption is that the coefficients are smooth. This is to make it easy to solve the SDE. So another assumption is that coefficients are smooth. So function x gives, let's say, sigma omega of x is smooth. I think, oh, okay, just try to use the same notation, okay? And I will also assume that the coefficients are uniformly elliptic. So this is the third assumption, that, let's say, A omega is uniformly elliptic. So that means that there is a certain constant, kappa, which is positive and finite, and such that we have a uniform ellipticity bound, something like kappa psi square is less than the norm of sigma omega of x psi square, and this is less than 1 over kappa psi square. And I'm assuming this is true for all x and all omegas. So for omega and for all x. So it's uniform ellipticity in the sense that it's uniform in space, but also with respect to the randomness of the environment. Okay, so that's one model. And eventually, I will be interested in what happens when we modify this equation by adding a local drift, which is constant. So we will also consider the equation that we obtain by adding a constant drift. And then the equation is modified. So let's say the direction of the drift is some vector, E1, just a vector. And I want to be able to tune the strength of the drift, and that will be the parameter lambda. So lambda is just a positive parameter. So what corresponds to the addition of a constant drift in this equation is the following one. Now I'm right an SDE, and now it depends on lambda. I will not indicate it depends on E1 because E1 is fixed. So when I start from point X, you get the same diffusivity coefficient. So the equation starts the same. And then B omega dt, and then the drift term. And the drift term has a lambda in front. And what corresponds to adding a constant drift is adding a drift term of the form A of, so A omega of x lambda omega x times t dot E1 dt. And this one also starts at time 0 from point X. Okay? So these are the objects we would like to study. And the question is to describe what happens to either x lambda or x when time goes to infinity. So we want to describe the possible scaling limits of these objects. So the aim is describe. It's the scaling limits. So let me just briefly outline what kind of results one might expect.
Excuse me, what is alpha?
There is no alpha, so it's an A.
How?
This is the same. This is a square of sigma,
Good.
and it is here. This is, I mean, this is what corresponds to adding a constant drift. Let's say this is the addition of a constant drift in the metric induced by A omega. But maybe I will come back to the form of this equation in the second lecture, when I discuss motivation. It is actually quite important that the drift term has precisely this form. So, yeah. So, I mean, you can rather easily guess what kind of results we would like to have. So let me just briefly mention them. So this would be something like expected results. So first of all, if you look at the case where there is no lambda, so in the case lambda equals 0, then, well, because of reversibility, you expect this process to behave like a Brownian motion, more or less. So you expect the process x omega starting from 0 at time t to be of order square root of t. And you expect to have a central limit theorem or invariance principle. Now, second thing is, now let's consider the case where lambda is not 0, where lambda is positive. So you add a drift of a fixed magnitude, lambda, in a fixed direction, and then you expect the process that you get to be ballistic. So what you would expect is that x lambda omega 0 of t should be of order t. And if you are optimistic enough, then you might think that you have a law of large numbers. Okay? So this is some kind of natural guess. And now you can do a little bit more and ask, what do you get when you scale t and lambda at the same time? So when you scale t and lambda at the same time, you are taking a limit in which, so you're taking a limit in which t tends to infinity and lambda tends to 0 in some way. So you make a very rough guess. You look at the equation for x lambda, and you see that the first part, the first two terms are diffusive. So the contribution of the first two terms should be something like square root of t. So if you look at x lambda omega at time t, you say, well, maybe first two terms will give me something of order square root of t. And the last term is ballistic term. So it's linear in lambda, and and in time it should be also linear. So you should expect two contributions, and then you see that there is a threshold when these two guys are of the same order. So something should happen when lambda t is of order square root of t. So you should look at the quantity lambda square t and see if this one. So when lambda square t is small, then this term should be dominant, and when lambda square t is big, then the drift term should take over. So we should distinguish the two cases. So let us write guesses. Let's assume that t tends to infinity, lambda tends to 0, in such a way that lambda square t tends to some alpha, now it's an alpha, which is not 0. So in that regime, you have the two terms are of the same order. So you expect some diffusive part from here and some drift part from here. Therefore, the scaling limit should be something like a Brownian motion, but with the addition of constant drift. So you would expect 1 over square root of t x lambda omega 0 of t to scale to, say, Brownian motion plus constant drift. Okay? Maybe. And there is a fourth regime corresponding, well, basically to the case where lambda square t tends to some alpha, but you also send alpha to infinity. And alpha is very big. Alpha tends to infinity. Because in that case, the drift part should take over. So you should start seeing the ballistic regime. So meaning that x lambda omega 0 at time t should be of order. It's linear in t and linear in lambda. So I'm meaning that this term should take over. So we should expect something of order lambda t. So this would be being already in the ballistic regime. And it turns out that if you have such a statement, then this is very, very much related to what we call the Einstein relation. Okay. So, lambda goes to 0. Actually, first we send lambda to 0 and t to infinity in such a way that lambda squared t converges to alpha for some alpha, and then we send alpha to infinity. There will be more precise statements later.
Then it's not ballistic.
Okay, if I want to be more precise, I take an expectation here. Let me say, at this stage, what I want to say is that there is a diffusive regime. So the diffusive regime should cover the cases where lambda squared t is going to some fixed constant. And if I take lambda squared t going to infinity, then I should see the ballistic regime. Which is, this is a little bit weaker than what I'm saying here. But what I'm saying here is that there is almost an overlap between the diffusive and the ballistic regime. So in particular, if you have such a strong conclusion, there is nothing in between the ballistic and the diffusive regime. There is no such thing like a critical case where you would see something else. Yeah?
What do you mean by ballistic regime? Ballistic is with positive spin.
Yeah, but yes, in this case, speed is going to vanish with lambda. Yeah. So what I mean is that you take that thing, you divide by lambda t, and then you prove that this converges to some constant. But you would, I mean, one way to get that result, which is not correct, but one way is to say, okay, I replace this guy divided by t by the speed. So I'm using the intuition of the ballistic regime, if you want. I'm using the fact that this term is the biggest one. Okay, so this would be a program for the course. Now, these results are not surprising. There is nothing strange in them. And, well, actually, maybe the only surprising fact in this story is that we don't know how to prove them. And more precisely, case 1 is okay. Case 1 was investigated in the 80s by many people in relation with homogenization theory. Okay, I will record the results in case 1. Actually, case 3 is also okay, under quite general assumptions. And this is an observation due to Leibovitz and Rost. But already case 2 is not, it's not clear how to get a law of large numbers. So there are partial results, which I will explain. Indeed, the position of the diffusion at time t will be linear with t. We can even be a little bit more precise, but the law of large numbers is not proved. And a fortiori, case 4 is also not completely understood. So there is one case in which we can complete the program, and this is adding a fourth assumption. So I will write it here, A4. So, which is the case where the law of the environment, Q, has a finite range of dependence. So if Q has a finite range of dependence, I'm not sure how to spell dependence. Then the law of large numbers was proved using regeneration techniques, ideas from the work of Alain Snitman, and well, in this particular case, it's a paper by Lian Chen. And then one has a hope to complete the program and get step 4, which indeed is what we recently did in joint work with Nina Gantert and Andrei Biatnitsky. So as far as case 2 and also case 4 are concerned, we need this assumption about the finite range of dependence. Okay? And the proofs involve different arguments. They involve some probabilistic arguments using martingales, etc., and regeneration. And they also involve some PDE arguments. And in particular, the proof of step 4 involves some PDE estimates, which are a little bit technical, and therefore I will discuss them in the third lecture. But they can be of some interest in their own. Okay. So what I will do now is focus on the first case, and if I have enough time also, I will discuss the third case, which are the cases which are better understood and for which we don't need the assumption that we have a finite range of correlation. So we focus on that equation with standing assumptions. Okay, so as I said, these are quite well-known results. And the reason why I want to review them is because they are part of the picture, but also because I will introduce a certain number of objects that will be needed later. So now I start considering only the case where lambda equals 0. In that case, there is no drift term. And the statement, the theorem, is that the scaling limit is Brownian motion with a certain covariance. So let us write it like this. I should have written some notation. So before I write the theorem, so some notation. So I write E. This is the expectation with respect to W. This is the expectation with respect to W for fixed omega, so the quench law. And I will write E with a double bar for the expectation with respect to both W and Q. So this will be the expectation with respect to W and Q. Wow, and omega. Okay, so this is the Uniled law, what people call Uniled. So I state the invariance principle under the Uniled law. Okay, so under this law, P, the Uniled law, then the law of the rescaled process epsilon x omega 0 at time dot over epsilon square. This converges to the law of some d-dimensional Brownian motion of d-dimensional Brownian motion with some covariance, which is not the identity in general, with some covariance. And I will call sigma the covariance that we get. So as I said, this is a result. I mean, these things were investigated in the 80s. So the first papers about this kind of homogenization statement for a random environment are due to Papanicolaou, Vardan, Osada, also the Russian team, so Urinsky and Koslov worked on related models for random walks. And you can make much better statements. So there are experts in the room about how to get quenched results. And under my assumptions, the quenched result is also true. Actually, it's under my set of assumptions, the quenched result is already proved in Osada's paper. Okay, and then there is one approach to this kind of result, which is in the papers of Kipnis and Vardan, and another paper by Demasi, Ferrari, Goldstein, and Wick, which is some kind of abstract version of this. And this is the point of view I'm going to adopt. So I will, so the presentation I'm going to give now is very much based on this paper of Kipnis and Vardan. Now, the proof in Kipnis and Vardan relies on the fact that you can approximate this diffusion process by a martingale. So what Kipnis and Vardan proved is that x omega 0 at time t, you can write it as the sum of two terms, mt and psi t. And in this decomposition, m is a square integrable martingale with stationary increments. Stationary increments. So actually, and a bit more, you have some control on the increments, etc. And anyway, M is such that you can apply the invariance principle for martingales to M. And then there is the other term psi, and this term psi, it's another process which does not contribute in the end. So the important thing is that the variance of psi, if you look at 1 over t times the expectation of psi t square, that goes to 0. And then once you know that, then you get the invariance principle. You apply the invariance principle to M, and you say that psi doesn't play any role, it does not contribute to 0. Okay, so I'm not going to prove that. I'm going to do something which is much simpler. It's in the spirit of Kipnis and Vardan, but I'm not going to detail all the steps of the proof, only part of it. So the starting point is to look at this diffusion process as using the point of view of the particle. So we define the process of the environment seen from the particle. Seen from the particle. Okay, so I have a certain space of environments, which I call omega. So here the space of environments is the space of matrix fields over Rd that satisfy the assumptions 2 and 3. So the environments are given by functions from Rd to the set of symmetric matrices satisfying A2 and A3, which were the assumptions about the regularity and the uniformity. And there is an action of RD on omega by translations. So you just translate the origin. I will use the notation D, which is a vector, D1, DD, for the generator of this action. And the notation for the action is X omega. So the translation of matrix field omega by X, I denote it by X dot omega. So this is the generator. And now the process of the point of view of the particle is you look at the environment omega, in which you are evolving, and you shift the origin to the current position of the diffusion process. So you look at X omega 0 at time t, acting on the environment. And that defines something. That defines, okay, call it omega of t. That defines a process with values in the space of environment. So we let omega of t be the environment seen from the position of the diffusion. And we have the process of the environment seen from the particle, and it's a process with values in omega. So this defines a process with values in omega. Now, it's a nice but not very difficult to prove observation that this process is Markov, and due to the reversibility assumption, you can also check that the measure Q is reversible, therefore invariant. And it's also not very difficult to prove from the uniformity assumption that it is ergodic. So the statement is that under P, and the process omega is Markov. So it's not only Markov, it's a very nice Markov process with continuous passes, so it's a diffusion process. And Q is both, so Q is reversible, invariant, and ergodic. Reversible, invariant, and ergodic. Now you should also observe that you can reconstruct the trajectories of the diffusion process from the observation of omega of t. So let me just use a little bit of notation. Now, I look at the coefficients in this equation. So sigma of x. Okay, I want to write that they are stationary fields. So sigma omega of 0, I will denote it by sigma of omega. And then the coefficient appearing here, sigma omega of x, will just be sigma of the translation of omega. And similar thing happens with this. B omega is also a stationary field. So B omega of x is of the form some B applied to x dot omega. And actually, you can compute what B is. B is 1/2 of some divergence of A, some divergence of A. And this divergence is a divergence operator on the omega space. So is the div, this is the adjoint of the generator of the gradient big D. Anyway, so with this notation, you can write the equation satisfied by the diffusion. Now, I make it start at 0, so x omega 0 of t. This is going to be the integral from 0 to t sigma of omega of s dws plus the integral from 0 to t b of omega of s ds. So then this is the way you get the diffusion back from the observation of the environment seen from the particle. And more explicitly, you see that x omega is an additive functional of the process omega. So this is an additive functional. Of the trajectory omega of dot, so to speak. So that's one point. I'm going to need the Dirichlet form of this process. So let me write it. The Dirichlet form of this process has the following form. So I denote it by E of f and g. So f and g are functions on omega. And the Dirichlet form is what you expect. So 1/2 of the integral of sigma df dot sigma dg dq with a certain domain, curly d, which is, in fact, the set of functions such that this is convergent. So the set of functions in L2. And when I write L2, I mean L2 of omega with respect to Q, such that df is also in LQ of omega and Q to the power d. And the proof of this is in the book of Olejnik, Koslov, and Zhikov. And later, I will also use the notation L2, 0 for the space of functions f which are in L2, so L2 of omega and Q. At some point, I'm going to drop the Q in the notation, which have 0 mean, so such that the integral of f dq is 0. And I will also need the space D0, which is the same, the set of functions which are in D and which are centered. The integral of f dq is 0. Okay, this is just notation that we will use a bit later. Okay, so now, having written this x as an additive function of omega, now what I want to do is not exactly to prove the central limit theorem or the invariance principle. I want to do something much simpler. I want just to compute the variance of x. Now you see, in the variance of x, there will be two terms. There is this term, which is not difficult. That's already a Martingale term. And then there is this term. So the first thing, which is an easy exercise, is to compute the variance of something of this form. So let us do it in the general case. I do computation of variance. So take a function f of omega, so values in R, and let us define the additive function af of t to be the integral from 0 to t f of omega of s ds, and let us compute the variance of this guy. So I compute the expectation at equilibrium of f of t squared. Okay, so you write what this is. Now this is a square of this integral. Split the integral into two parts, you get a 2. Integral from 0 to t, du, integral from 0 to u, ds. And then you have the expectation of f of omega of s, f omega of u. Okay. Now, I have a stationary process, so I can change this term, write f omega of 0, f omega of u minus s. Then you change variable, so you replace s by u minus s. That's it. And finally, you get that this is twice the integral from 0 to t du. Then you have to integrate u between s and t. So this is multiplied by t minus s, t minus u. And this covariance, f omega of 0, f omega of s. Okay?これは本当に簡単ですね。Nothing difficult. I want to do one more thing. I want to divide by t. So if I divide by t, I have 2 over t here. And then this t becomes a 1. And I divide by t. Okay. Anyway, so it's quite simple. Now, we are interested in what happens when t goes to infinity. So the first thing we can say when t goes to infinity is that this is going to be non-decreasing, right? Because when t goes to infinity, okay, so that term is non-negative because the semigroup is symmetric. So when t grows, you integrate over a larger domain, and this is also a non-decreasing sequence. And you can even send t to infinity in that expression. So you get that the variance at the limit. So if now I take t to infinity, this should converge to twice the integral from 0 to infinity du 1 times the expectation of f of omega of 0, f omega of u. I guess this was a u. Or I don't know. Or maybe this was an S. Never mind. Okay. Now, the limit might be finite or infinite. We are interested in cases where the limit is finite. So we get a finite limit if and only if the integral from 0 to infinity of du times the expectation f omega of 0, f omega of u is finite. And so this condition, let me give it a name because it plays a role. I will call that the H-1 condition. So just a name for the moment. Okay. Now, that was some kind of easy computation, preliminary computation. And now I wish to apply that to X. So that's a general computation. Now I want to apply this to check that the process X has a limiting covariance. So what we check is that 1 over t times the expectation of x omega 0 at time t in some direction e, dot e, squared. I want to check that this has a limit. And then this limit will be the limiting variance sigma of the limiting Brownian motion in the direction e. Okay? So let us deduce that this has a limit from this h-1 condition. So I go back to the expression of x, omega of t, as the sum of these two terms. So the martingale term, sigma omega of s dws, and the other term, which has a b, omega of s ds, which is of the previous form. Okay?
Excuse me, if you say h-1 condition, I guess you assume that the finite was some class of function there.
Yeah.
For which class you have in mind? It's L2.
Oh, well, for the moment, the only thing I know is that there is a limiting variance if and only if this condition is satisfied. The computation is for NEF.
No, but the condition is not for.
But the condition is not for NEF. No, of course, there is some restriction. So that is, for the moment, I'm just writing it as the h-1 condition, and in the moment we will look at the space of all functions that satisfy this. It will be some. I mean, I call it the h-1 condition because in a moment I will explain that h-1, so the space of functions satisfying this, is actually the dual space of some h1 space. But indeed, it's a restriction. It's a condition on f. Condition on f. So let's say if this is satisfied, then f satisfies the h-1 condition, and it will. Okay. And actually, if we want to compute the variance of this, we should check that this one is in h-1, satisfies, that b satisfies the h-1 condition. Okay? But I want a little bit more because I want to prove that if I take the square of that, take the expectation and divide by t, then I do have a limit. Okay. So let us do it. There are many ways to do it, but I want to do it using symmetry properties because symmetry properties will pop out quite often in the talks. So the symmetry properties are the following. If you reverse time, you look at what happens in this equation when you reverse time. So reverse time. So reverse time means that, say, you fix the time t, and you look at RT. So this is supposed to be an R. This is a time reversal operator on the space of actually continuous trajectories defined from 0 to t with values in omega. So you just, if you take a trajectory omega, when you apply it, when you reverse time, so you compose it with RT, and you look at time s, this by definition is omega at time t minus s. Okay? Now, by reversibility, the law of small omega, the process of the environment is invariant under RT. So I write it, it's a little bit loose, but let's say that P is invariant under RT. Now you can compose with RT here and look at what happens. So what happens is that when you reverse time here, you don't change anything. Instead of integrating from 0 to t, you integrate from 0 to t. So that doesn't change. So that part, that one is symmetric. Symmetric means invariant under time reversal, RT. And then you time reverse this guy, and that guy, when you time reverse, is antisymmetric. The sign changes. This one is antisymmetric. Okay. I guess this is clear. If you look at what is X, let's say you look at, you want to compute the position of the diffusion from the observation of the process of the environment seen from the particle. So what you have is that, by definition, omega of t is the translation by x omega 0 of t of the environment at time 0. Okay? Now, if you time reverse, then that one becomes omega of 0. But omega of 0 is what? This is the translation of omega of t by minus this guy. So this is minus x omega 0 of t applied to omega of t. So if you time reverse the evolution of the environment, then the effect on the position of the diffusion is just you take a minus sign. You're going backward in the other direction. So this is an antisymmetric additive functional. This one is obviously a symmetric additive functional, and therefore they are orthogonal. So as far as the computation of the variance is concerned, then you get that the expected value of x omega 0 of t, I have to take things in some direction e. So when you square that, and you take the expectation of this additive functional over there, which I'm going to write with this notation a b dot e of t squared. So this is the expectation of the martingale part, the integral from 0 to t of sigma omega of s dot e dws squared. Okay, yeah, so I'm using the fact that this one is symmetric, this one is antisymmetric, and therefore the cross product vanishes. They are orthogonal. Now you look at this. So first, this is something. This is a martingale with stationary increments, so this you can compute. This is just t times the mean value for q of sigma dot e squared. Okay. All right, and now you can divide by t. So let's divide by t. 1 over t, 1 over t. And here we get 1 over t. Okay? And this is constant. Okay? Now, the conclusion is the following. If you only look at that term, then this term is going to be bounded by something, by q of sigma e squared. So that means that this field, b of b dot e, it does satisfy this h-1 condition. So the conclusion is there are two. First of all, that b dot e satisfies this h-1 condition. And there is another conclusion, which is that, okay, we saw that this term is non-decreasing, therefore that one is non-increasing. So it converges to a limit. So 1 over t times the expectation of x omega 0 of t dot e squared, it decreases to some limit. And that limit defines the matrix sigma, because you do it in all the directions, and you see that it's linear, and therefore there is a certain matrix sigma, so that this limit has the form sigma applied to the direction E. So this is the proof that the limiting variance exists. It does not quite prove the central limit theorem or the invariance principle. But it's not so far from proving it. A little bit is missing. One remark I should have done when I stated the theorem is that you can check that, and you should check that sigma is non-degenerate. Okay. Okay, so that was the first thing I wanted to do. Do you have any question? Did someone ask? Yeah. We can make a 2-3 minutes break if you want now. It's a nice moment. And then I should. So is it okay? No question. All right. So now let us discuss this H-1 condition in more details, answering your questions. So I keep the condition. Okay. Now, so I want to discuss H-1. So look at the function f, which is in L2, centered, and satisfying condition H-1. So you, in the H-1 condition, what is hidden is the semigroup of the process omega of dot. And if I write, say, L, the generator, so something like 1/2 this divergence operator times A times D. This is the generator of the process omega of dot. Okay. Then you can see that F satisfies H-1 if and only if. So it satisfies H-1 if and only if F is in the domain of L to the power minus 1/2 is in the domain of, let's say, minus L to the power minus 1/2. So in a dual form, this is the case if and only if, when you look at the sup over functions g which are not identically 0 of the integral of f g dq squared, let's say, and you divide by the Dirichlet form, e of g and g, then this is finite. Because this is a dual norm corresponding to minus L to the power 1/2. Okay? So in that sense, H-1 is a dual space of some H1 space, which is the domain of E. So in a slightly more formal way, we introduce the following spaces, which are the Sobolev spaces. So first we define H1. And the definition of H1 is as follows. So you look at E on the space D0, which is a space of functions with square integrable gradient, which are also centered. And that's a norm on D0. And it's a norm because of ergodicity. The only functions on which the Dirichlet form vanishes are constant functions. So this is a norm. And then H minus 1 is the completion of D0 with respect to that norm. So H minus 1 is the completion of D0 with respect to the norm induced by the Dirichlet form. And H minus 1 is the dual space. So this is the dual space, where the product is just the L2 product. So a function which is in L2, 0, is going to be in H minus 1, or you can identify functions in L2, 0 with elements of H minus 1, if and only if this is finite. So I can see functions satisfying this condition as a subspace of H minus 1. And I will call that subspace the intersection of L2, 0 with H minus 1. So this is an abuse of notation. So with an abuse of notation, I will denote by L2, 0 intersected with H minus 1. This will be the set of functions f in L2, 0 that satisfy that condition. So such that the sup over G of this thing, the integral of ft dq squared divided by E of G is finite. Okay. And H minus 1 is in principle a bigger space. It contains elements which need not be functions in L2. Both H1 and H minus 1 are spaces of distributions. But this subspace is dense. This one is dense. What else did I want to say? Well, okay, there is a norm. So I will write it like this. If I have an element of H minus 1, I write norm in H minus 1 like this, usual thing. And this norm is is this thing. So that means that from the computation over there, it follows that, let me write it here. So what the computation over there shows is that when f is in L2, 0 intersected with H minus 1, then when you look at the variance, 1 over t times the expectation of AF of t squared, then this converges to something, as this something is exactly twice the H minus 1 norm squared. It converges to 2 times the norm of f in H minus 1 squared. And now the Kipnis-Varadhan invariance principle extends to all functions in H minus 1 intersected with L2, 0. And actually, it also extends to H minus 1 itself. But this I will discuss in 1 minute. So the same theorem by Kipnis and Varadhan, but in this more abstract setting, says that if you look at the law, so first you choose an f which is in L2, 0 and in H minus 1, and you look at the additive functional under P. So under P, the law of the rescaled additive functional, epsilon AF at time dot over epsilon square, this converges to a Brownian motion, to a one-dimensional Brownian motion, with some variance well, and the variance is the limit of the variance, and this is twice the h minus 1 norm. So just for notational purposes, I write sigma of f for the variance that is twice the norm of f in h minus 1 squared. Okay? And the proof is based on the same martingale approximation. So in the proof, which I don't do, which I don't detail, then you also do the same thing. That is, you write AF of t as a sum of two terms. One is a martingale term, so a square integrable martingale with stationary increments, to which you can apply the invariance principle. And then another term, psi t, which has a vanishing variance. And moreover, if you look at the proof, you see that this guy, so it has a vanishing variance, 1 over t times the expectation of psi t square tends to 0. But it's also, now it's clear from this expression that psi is an additive functional. And in fact, it's, as before, it's going to be an antisymmetric additive function. So in the proof of Kipnis-Varadhan, when you construct the martingale part with an approximation, and psi by the same approximation, and then you see that psi is an antisymmetric additive functional. And so the structure is the same as the computation we did for X. Just an extension of that. Okay. So that is okay for functions, but there is no reason to restrict ourselves to functions. In fact, the theorem over there works on h minus 1. So the true statement is without this. Okay? I should be a little bit more precise about that, because the process AF is defined as the integral of f of omega s ds. And if f is a distribution, then before stating the invariance principle, one should check that it does make sense to consider the additive function AF. And so there is a lemma that does this kind of things for you. And the lemma says the following. Okay, so for the moment, let us assume that f is a function, nil to 0, also in h minus 1. And then I claim that for all time t, we have an a priori estimate on the variance of AF. No, not only AF, because we want to define AF for all times. So we should be a little bit more clever, and we should look at the sup over a time interval of AF of S squared. Okay, so there is an a priori estimate of this in terms of the h minus 1 normal of F. And I think that the bound is 8 times T times F h minus 1 squared. Okay. Well, I guess this is correct. Okay. So that lemma is quite useful. So first of all, it tells you that if
Excuse me,
Yes.
is it the supremum of square of square of supremum? Which do you mean? Left hand side.
I guess both.
Okay.
It doesn't mind.
Okay.
What I do mean is that the sub is inside
okay,
the
sorry.
expectation. Yeah, okay.
Okay.
So,
But here, a priori, f is not negative.
no. No. It cannot be non-negative actually because it's centered.
So they're different. Square of
But
supremum.
I think, yeah. So maybe it would be better like this. Probably all right. Because I want to say. Anyway, it would work for both.
So this is strong.
Sorry?
This is strong.
Which one is the strongest one? The one with the parenthesis here is stronger. So the one I wrote is stronger. Yes, and okay. And this is the way we wrote it in the paper. So, yeah, and it's okay, like this. It's true. Okay. We can ask Fukushima Sensei. I think that これは福島先生の本で言いますか?
I forget.
I think it is. Actually, a similar lemma is also in the paper of Kipnis and Varda, but I think that it is in your book, or something a little bit like this is in the book. Anyway, so this is interesting in many respects for us. So first of all, it's quite kind of clear that once you have something like this, you can take an f which is not in L2, you take it in h-1, you approximate it by functions f which are in L2 and in h-1, and then you see that things are going to converge. You will get something in the limit, you will get some process, so you can use this estimate in order to make sense of AF when f is in L2, is in h-1 and not necessarily in L2. So use to make sense of AF when f is in h-1. And but this is even more useful than this because you can see that this almost tells you immediately that if you rescale AF this way, then you have a tight sequence of processes. This is a kind of control on the fluctuations of AF that we need in order to get the tightness in the invariance principle. And it's even more useful than that because you can use it to show that the martingale approximation of Kipnis and Varabhan works. Okay, so let me so let me just make one remark on the proof. I'm going to sketch the proof. There are different proofs, and I'm going to sketch the proof very quickly. And because one way to prove that is to use a martingale argument using forward and backward martingales. So the key of the proof, so to speak, is to find a martingale empty. So there is a martingale such that you can write AF at time s as a sum, so 1/2 of the sum of two martingale terms. One is just ms, and the other one is a term that you obtain when you reverse time. So when you reverse time, you get something. And okay, so I'd better write exactly the term. So this is m composed with time reversal at time t and evaluated at time t, minus m composed with time reversal and evaluated at time t minus s. Okay. Something like this. And you can see that playing with the fact that AF, so I wrote AF as martingale plus this antisymmetric term. So you apply time reversal to this thing doesn't change. That one is changed by R. That one is going to change sign. And then you sum the two things and you, in order to cancel the contribution of psi, and then you get something like that, and actually you get something like that. I guess that this M is the same as this one. Okay? And once you have this, then you can make the computation. So first of all, for the same orthogonality relation, you see that the expectation of AF at time s or t squared plus the expectation of psi t squared. This is the expectation of mt squared. So let me write like this, mt squared. So and then I can divide by t, and I can let t tend to infinity. So that term is constant. Okay, this is the bracket of the martingale, and that one goes to 0. That one goes to twice the h-1 norm. So from that you get that sigma of f equals 1 over t times the expectation of mt squared, which is constant. Okay? And so that's one observation, similar to the one we did when computing the covariance of x. And also, from that decomposition as a forward plus backward martingale, you can use Dup's inequality. So when you use Dup's inequality, you see that when you take the sup in L2 over some time interval, you will get exactly this term, the expectation of mt squared, and that will give you this sigma of f. Okay, and the 8 comes from the computation. Okay, so you apply Dup's inequality. And so you apply Dup's inequality to both terms. So in particular, you get that the expectation of the sup over s of ms squared when s is less than t is less than t times. So I wrote it with the h1. Okay, so let's write it with the h-1 norm. So 2 times t times f h-1 squared, and then the same for the second term. Okay, and then you get this thing. Okay. Now, okay. So this was more or less what I wanted to do about what was the first step in my plan, that is getting the scaling limit of x without the drift term. So okay, so we've seen that if you rescale the process x omega 0 in a diffusive way, then this converges to Brownian motion with a certain sigma as a covariance matrix. And we've seen something better, which I just erased. But we also saw that if you look at epsilon times an additive functional AF that you also rescale in a diffusive way, then you also get a Brownian motion. And now the covariance is called sigma of F. And we actually have more. I mean, these invariance principles, they come from martingale approximations. So, for instance, you can combine the two of them. You also have conversions like this. Well, this is not very well written. So let me write it in a better way. We have all the joint central limit theorems or invariance principles we wish to have, we have them, because each time we can replace this, approximate this by a martingale, approximate this by a martingale, so we have a joint martingale approximation for the two terms. Now, if I want to be a little bit more precise, if I look at the joint law of this one and this one, I will get a Brownian motion. This is in dimension d plus 1. And the covariance we can compute it. So the covariance arising from this guy is sigma. The covariance arising from this one is sigma of F. But we should compute the covariance between the cross term, the covariance between this and this. But once again, since this is an antisymmetric additive functional, and since this one is a symmetric additive functional, they are orthogonal. Therefore, the terms here just vanish. Okay. So that is the answer to case 1, the case without the drift. In the remaining time, let me discuss how this actually also covers case 3. So case 3 is the case where we are scaling time to infinity, and at the same time, we let lambda tend to 0, but in such a way that lambda squared t converges to some alpha, which is finite and not 0. Okay? And so the rough computation in the introduction of the talk showed that in that case, the diffusive term and the drift term are of the same order, and that the limit, so first of all, the scaling should be the same as here, and the limit should be some Brownian motion, but now with drift, with a constant drift. So let me just briefly explain why this is true and how this follows from that. So okay, so let me just rewrite the equation for the process at hand, which is now x lambda omega. So if I write it, I can, okay, I write it. This is sigma omega x lambda omega 0 at time t dwt. Then I have first drift, b. And then I have this lambda E1 dot A omega x lambda omega 0 at time t dt. Okay? So in order to compute the scaling limit of this process in this regime, we express it in terms of the process without the lambda using the Gersonov formula. So the Gersonov formula tells you that for a reasonable function and for a fixed omega, if you take the expectation of some function of this path, x lambda omega 0 at time s, when s is less than t, just look at a nice function on path space with a lambda, then you can express that as an expectation of the same thing for the process without the drift. I just wrote the same thing. But here you have to include the Radon-Nikodym derivative. And the Radon-Nikodym derivative will be an exponential martingale. So it's an exponential of something. It depends on lambda in a linear way. So there is a lambda. And then you have some martingale. So I call it B bar at time t. And you have to subtract lambda square over 2 times the bracket of B bar computed at time t. Okay? And what is B bar? Well, B bar is what you should include to have the right, to produce the right drift term. And so you just check that B bar is the integral from 0 to t, sigma, omega, x omega 0 of s, dot E1, dws. And then the bracket is just the integral of this, the square of this. I think this is okay. Yeah, this is okay because when you take the bracket of this with x, then you have sigma over there, you have sigma here, so you get the square of sigma, which gives this a, which is over there. Okay. Now, let us use this formula in order to get the scaling limit. So now I'm going to take the unit average of some function. So f is a nice function, a continuous function on path space. And I'm applying it to the rescaled process, so I put an epsilon, x lambda omega 0 at time s over epsilon square, where s varies between time 0 and time t. Okay, so here I'm going to scale time by a factor 1 over epsilon square, and I have lambda. My condition, the regime in which I want to study this limit is when lambda square t tends to infinity. In terms of epsilon, this means that lambda square over epsilon square converges to alpha. Okay, so we use the formula over there. This is the expectation of f of the same thing, just without the lambda. Times the weight, which is exponential lambda. Now I have to compute B bar at the last time, which is t over epsilon square. And I have to subtract lambda square over 2 brackets of B bar also at time t over epsilon square. Okay. So far, so good. And then we can pass to the limit. So we pass to the limit using some joint invariance principle, a bit like this one. So we want to pass to the limit. You see, everything is on the right scale. The limit of this we know, and the limit of this we also know because lambda is of order 1 over, no, lambda is of order epsilon. So this is like multiplying by epsilon. And then there is an invariance principle for B bar. And for the same reason as before, there is a joint invariance principle. So you apply the invariance principle for the joint process x omega 0 and the martingale B bar. Okay. So you can do that. Well, you should just pay attention to the fact that this is not a bounded function, but it's not difficult to pass to the limit. And then you get the limit. And so the limit that you get when you do that is something of the form, the expectation of f of the first component that arises in the joint central limit theorem. Let's call it Z1. So some Brownian motion taken at time s for s between 0 and t. And then you get the exponential of, now I have to take into account the alpha. So I get square root of alpha times the second component. Let's call it Z2 times t minus alpha over 2. And let's say the bracket computed at time t. So in that expression, bracket is a very, okay, it is a bracket, but Z1, Z2 is just a Brownian motion. The couple Z1, Z2 is a d plus 1 dimensional Brownian motion. Okay? And this expression, so this is just, you have a Brownian motion, and well, this is also a Gersonov transform if you want. We can invert the Gersonov formula, or this is a shift in Cameron-Martin space also. So when you tilt the measure by an exponential of the Brownian motion, you get a Brownian motion with a drift. So this is also the expectation of same function f, now applied to the process z1 of s plus some drift term, which should have a name. So I should give it a name. Okay, some drift term. Let us call it mu s, but we're going to compute it. So anyway, so I mean, this is just to convince you that the scaling limit is Brownian motion with a constant drift for some mu, but in fact, we can compute all the terms. So we should compute first the variance of Z1, Z2. So let us compute the covariance of the couple Z1, Z2. This is a d plus 1 dimensional matrix. And as before, so Z1 corresponds to X, so the covariance is sigma. Here there is something I don't care about. And here, well, the term you get here is the limit of 1 over t times the expectation of x omega 0 of t times b bar of t. It's covariance. And now, look at the expression for b bar, and you see that b bar of t, this is x omega 0 of t dot p1 minus the drift term minus the integral from 0 to t b omega of x omega 0 of s ds. Okay? Now, once again, when we compute the covariance, then we see that you'll get two terms, but one term will be the covariance between x and this additive functional, and because the first one is antisymmetric, the second one is symmetric, they are orthogonal, therefore this term vanishes. So this is exactly 1 over t times the expectation of only the first term remains, which is x omega 0 of t times x omega 0 of t times E1. And so when we pass to the limit, this is given by sigma. This is sigma applied to E1. So this is a non-diagonal term. Here we get the sigma E1, and here we also get sigma E1, and gets transposed. Okay? So that's the covariance of Z1, Z2. And now, if we want to compute this mu, it's going to be sigma E1, because this mu in this expression, this is the bracket of the two components, Z1 and Z2. So with the square root of alpha, so mu is square root of alpha times the bracket of the two things, that is the expectation of Z1 of t, Z2 of t divided by t, if you want. So this gives this term, right? So we get square root of alpha times sigma E1. Okay. And so that's the expression for the drift that we have in this scaling regime. So let me write the conclusion. Okay, let me write this. This is theorem. So as I said in the introduction, this computation, this observation, it's taken from a paper of Leibowitz and Rost, I think from '94. And so the conclusion is the following thing. So in the scaling where lambda is proportional to epsilon. So let me just okay. So you look at the law under P, the law of the process epsilon x lambda omega 0 at time dot over epsilon square, but with lambda square over epsilon square equals alpha, for some alpha. So you fix alpha first. Maybe it's better to say let alpha be some number, and then I look at the law of the rescale process in the scaling I was considering. So that thing converges to the law of Brownian motion plus constant drift. And the Brownian motion has covariance sigma, and the drift is given by this square root of sigma, etc. So the covariance is sigma, and the drift is the square root of alpha times sigma in the direction E1. Okay? And just to finish, is it okay?
So,
I mean,
I do not completely understand the equality in the from you in the above the last one. I mean to deduce. Sorry, the above one.
this one?
Further above.
This one?
Okay, the top. Yeah, this one. So yeah, I understand how you compare the.
Sorry, you
from this to be.
from this to this?
Yes.
This is one way to answer your question is so this is Brownian motion plus drift.
Yes, yes. Yeah.
Now apply the Gersonov transformation,
right.
And you get that.
Yeah, but so it's how to say the process is inside it, and data you?
So you mean Z2 and Z1 are correlated.
Yeah,
So you can decompose Z2 into Z1 plus its orthogonal component.
Can do that. You can say it's a Gaussian transformation if you want. A little bit pedantic in this context, but okay. You can say it's you can say it's a Gaussian integration by part formula.
Right. Okay. No, it's
And actually, if you want to be very pedantic, you can say this is some kind of Maliavin calculus, but
yes. Okay.
very
I have another question. You said the Eva satisfies the variance principle. Is it from that formula above?
If you want.
That's the integral of sigma.
Yeah. So the definition is that B bar is given by a stochastic integral.
Yes.
Okay. So let me write this in terms of the environment seen from the particle. So I get sigma omega of s dot E1 dWs. And it's also clear from this because it's a martingale. And the bracket, is the integral from 0 to t of the square of this.
So you can use the standard martingale D.
Yes, absolutely. Yes. You can use the martingale CLT, so you can use the ergodic theorem for this guy. You can use the martingale CLT. And actually, this one, when you scale, it scales to a Bernoulli motion. And the variance of this Bernoulli motion is just Q applied to sigma dot E1 squared. So this is the variance you get.
So I have another question. Can you do quenched in this case?
I think so, but yes, I think we can do it quenched, but we need some estimates,
Right.
a priori estimates, and I will discuss some estimates. No, yeah, I think so, and I think that this is not very difficult. I think that the a priori estimates that you need are not very difficult.
Right. Yeah.
Maybe I have one remark like this, not exactly about the quench problem, but so I gave this proof using Gaussian transforms, which is a natural proof for probabilists. You can also prove the same kind of statement using homogenization arguments. There is, you can look at the process x lambda, you rescale it, and you look at the generator, and you prove some homogenization theorem about I mean, looking at the generator of x lambda when you rescale it. And that should be possible. I mean, I'm sure this is possible, but it's not written as far as I know. But and it's possible because then you introduce a corrector, and the corrector is the same. Actually, the corrector for without the lambda is also a corrector when you introduce lambda in this scaling. So there also should be an homogenization proof of this result. Okay. Any other question? Yes?
Hi, maybe a naive question. So for all the results that you showed here today, is it straightforward or possible to use these results to say something about random walks in random environments by some sort of embedding argument in the martingale?
No, I don't really think so. But what happens is that the same results, similar results, are true for random walks with random conductances. And the proofs are the same. I mean, the proofs for the case of diffusion processes adapt to the case of discrete random walks on the grid with random conductances. So you consider random walks with random conductances because you want to keep the reversibility. But I don't think you can I'm not sure you can go from one model to the other one directly. But you can just repeat the proofs or mimic the proofs. And this is done and this exists in the literature.
Sure.
Mm-hmm. Any other question? No? So let me just take the last 2-3 minutes to state that, in fact, just as we can just as we for the central limit theorem, we got the central limit theorem for the position of the diffusion, but also for an additive function of the form AF. Then in this statement, you can also include an additive functional. So I'm just writing some extension of this Lebowitz and Ross theorem. Now, if instead of looking only at x, I also take a function f or a distribution in h-1, and now I look at the law, so under P, and you look at the law of the joint process where you keep x lambda omega 0, you rescale time, and you add the additive functional. So epsilon AF at time dot over epsilon square. Then you can play the same thing. So we are still in the same regime where lambda square over epsilon square equals alpha or tends to alpha. And then we pass to the limit in this thing, and we also get a Brownian motion with the drift. So this converges to the law of same thing, Brownian motion plus constant drift. And now we need to express the covariance and the drift. And the covariance, so the covariance is like this. You have the covariance sigma for the first component. The second component has some variance, sigma of f, which we saw is the h-1 norm. And the other terms vanish, once again, because we have an antisymmetric and a symmetric additive function. Okay? And you also have the drift term. So the drift term of x is what it was before, sigma E1. And here we get something. We get something. And this something, let us call it gamma bar of f. Okay? And now I can do a little bit of computation. So once again, well, this gamma bar is what? It's it arises just like in the hidden blackboard. It arises as a correlation between different terms. So gamma bar of f. This is the limit in time of the covariance of AF in time t and the martingale part B bar. And if I do the same computation using the formula that you still can see over there, then you see that now it's going to be different because AF is symmetric, so we only keep the symmetric part. So we get the covariance of AF of t with the symmetric part, which is minus A B dot E1 of t. And I think that there is a here I forgot to take the scalar product with E1.
I think expectation should be divided by t.
Yes. Thank you. So this is this thing. So okay, so this is the product of f and b dot E1, the scalar product in H minus 1, minus the scalar product of f and b dot E1. This is in H minus 1, H minus 1. So I use the notation for I mean, just as we wrote sigma of f for twice, sorry, this is probably twice the scalar product. So sigma of f was twice the H minus 1 norm squared. And then I will use the notation sigma of f and g for the bilinear form, which is twice the scalar product of f and g in H minus 1, H minus 1. Okay? So with this notation, then this gamma bar is nothing but minus sigma of f b dot E1. Okay? So we get certain expression as a covariance. All these sigmas are covariance operators which arise, and everything can be expressed in terms of these sigmas. Okay. So, thank you.